All right, so this is the chapter 9 from lecture number 1. And so chapter 9 is talking about bonding. And so we've talked a little bit about bonding before. We've talked about making cations versus covalent bonds. And so today what we're going to look at is we're going to look at the theory behind why these bonds form. So bonds happen because when elements combine, they combine to form compounds. And so a compound is any type of material where we have two or more elements kind of coming together. And the neat part about that is each of those compounds can have entirely different characteristics from the elements that they're starting from. So the bonds that we are talking about, this bonding, are the chemical bonds that are going to hold these new atoms together to form these new molecules. Right? So as atoms get put together, they're held together by these chemical bonds, and that's what forms our molecules. So chapter 9 is focusing on what we call bonding theories. And so while we might have known about these bonds, we haven't talked about why or how they form, and so that's what we're going to look at in this one. So they're explaining why and how the atoms attached. They give us the idea about why some atoms combinations are stable and others aren't. And then we're going to use this to help us start to predict the shapes of molecules. And then we can use those shapes to help us predict chemical and physical properties of our different compounds. So the first one that we start with is called the Lewis bonding theory. And it's one of our simplest models. Now, since then, our bonding understanding has evolved, and so there are more advanced models, but the Lewis model is a good one for us to start with. And Lewis theory basically emphasizes the valence electrons. So he ignores all of those core electrons, those ones in the lower energy levels, and focuses only on the electrons in the outermost energy shell. For Lewis theory, we draw something called Lewis structures. They can also be known as electron dot structures, and they give us the ability to help predict how these molecules are connected, how the atoms inside the molecules are connected, where those electrons might be for their valence electrons. This gives us an idea about the molecule's stability, shape, size, and polarity. And so that's the basis of the Lewis theory, is us being able to understand it and form these Lewis structures or electron dot structures. And so in Lewis's theory, the reason why atoms bond is that chemical bonds form when there's a lower potential energy between the charged particles and the atoms that they're making. So this chemical bond is better when they're together than when they were apart. So our atoms, as they start to interact, they prefer this bonded part. It's a lower energy state than when they were individually there. So there's three parts that we look at for that. We look at what we call the nucleus-nucleus repulsion, the electron-electron repulsion, and then the nucleus-electron attraction. And so if we were to think about that, a nucleus to nucleus, this is a positive and the positive. And so that means that each of those two nuclei from the atoms need to be a certain distance away from each other. Because they're both positive charges, then they repel each other. So as they come closer, then they will start to push each other away. So there's only so far we can bring them before they end up pushing too far against each other. Our electron-electron is because these are negative and these are negative. And so as our electrons travel around our nuclei, the electrons also want to keep a certain distance or space between each other, because they don't like each other, or they repulse each other because of their charge. But the benefit of why a bond might form, because so far there's been no reason, no attractive force pulling those two atoms together, is that there's an attraction between the nucleus to an electron. Because the nucleus is positive and the electron is negative, then there's an attractive force that can form between them. and that will hold that electron to that nucleus. Now, when we bring this other nucleus closer, there's also an attractive force that can form between that electron and that nucleus. It's that attraction between the electron to both of the nuclei, which can be why a bond, a chemical bond, can form between those two atoms, is that those electrons may like that attraction between the two nuclei instead of just the one, and that might help us overcome those nucleus-nucleus repulsions and those electron-electron repulsions. And that's how they find those, that's how a chemical bond can be formed. Now, there's three types of chemical bonds. We have ionic bonds, which is pretty much a charge attraction between ions. So that's a positive ion and a negative ion. We have a covalent bond that can be formed, which is where we share electrons. And then we have a metallic bond that forms, which is really like the electrons move freely between all of the metal atoms. And so we've talked about this before. And so we wanted to make sure that we have them classified. An ionic bond is going to be a metal and a nonmetal. And those electrons are going to be transferred from one to the other. A covalent bond is between a nonmetal and a nonmetal. And those electrons are going to be shared. And then lastly, we have a metallic bond, which is when we have just metals. And the electrons basically exist as a giant pool between them. Now, as we've gone through, we've kind of come up with these different ionic and covalent bonds. And so we've talked about those before. If you need a refresher, there is some on those next couple slides. But one of the things that we're going to add now is that we're going to be using our electronegativities to start to give us some classifications for inside of there. So when we share our electrons, those electrons might not be even between them. And so we're going to start to eventually start to get into some more of that fine tuning of these different types of bonds. So we'll talk a little bit about how we can talk about bond strength for ionic bonds first. And then we'll talk about what we can do with our covalent bonds and how we can fine tune between them. So one of the first parts that we're going to talk about is we're going to talk about crystal lattice structure, right? And so to get us on that idea, I want you to think about this question. If we were to perform the reaction, so we have KCl as a solid, and we're going to separate the anion from the cation, the K plus from the Cl minus. So we want to think about, is that going to release energy, take in energy, or not have any change? Now, you might not have known what your answer should be. And so I want to rephrase that question. If you had two magnets that were held together, positive side and negative side, what would happen? Do the magnets separate by themselves? Do we have to put in effort to pull the magnets apart? Or the magnets come apart and stay together with no effort in either direction? And so you can try this. Go get two refrigerator magnets. You can stick them together and then try to take them apart. Now, our atoms work in the same way when they're going through an ionic bond. They have that positive side, which is our cation. They have their negative side, which is their anion. And when they're forming that chemical bond, that ionic bond, then they're stuck together. So when we go back to our question, this is us saying that they will be coming apart by themselves, right? Which isn't what we see with our magnets. This would be us saying that we would have to pull them apart, which is what we see. And that's why that's going to be our answer. And the third one is saying that it doesn't take either energy one way or the other. And that would be that if we put those magnets together, they would be very easy to put together or take apart. They're like not interested in each other. Kind of like if you had two pieces of paper next to each other. And so we're looking for B there for our answer. Now that concept with the magnets is the basis of our energies for our ionic bond formation. When we try to ionize something, when we want to take away an electron, that requires energy from us. That's going to be our endothermic process. When we want something to pick up an electron, especially for a nonmetal, then that can be exothermic. It can release some energy for us. Now, normally the ionization energy of the metal is larger than what we get back when we form the anion. And so the formation of an ionic compound should be endothermic. It means that it should take in energy. However, when we look at making something like NaCl from its elements, its heats of formations, a lot of times what we notice is that they're exothermic. And so we're not sure why that is. Because right now, it seems like it should be harder for us to put them together because it takes more energy to make the cation than we get back when we make the anion. And that's because we're not including the ionic bond that forms. So when the crystal forms, when our ionic compounds form, there's this extra energy that's released from the cation getting surrounded by anions and the anions being surrounded by the cations. This is called the crystal lattice. And so it's held together by that attraction between the cations and all of their anions. So when we make our solid crystal, we're really trying to form this crystal lattice that kind of maximizes all of those attractions. Because the more attractions we have between the positive cation and the negative anions, the stronger that crystal lattice becomes, the more attractive forces it feels. And so this is a picture of a crystal lattice. So this is going to be if we only had the ions separated and moving around. And then this is when the ions form the ionic bonds, which is them being inside that crystal lattice. So the part to remember with ionic compounds is it's not just one Na plus and one chlorine minus coming together. It's not directional. It's really that this green chloride is interacting with all of these other purple sodiums. And then those purple sodiums can interact with a lot of other chlorides, and that process repeats and repeats and repeats. So there's no such thing as an ionic molecule. Instead, we just have the empirical formula. We have the lowest ratio between them, but it's not like you just only have one sodium and one chlorine by themselves generally. Normally they exist as this big collection of crystals. So that extra energy that's stabilizing our crystals from forming, that's going to be our lattice energy. And so that's why the formation of most of our ionic salts is going to be exothermic, is because the lattice energy is the energy required to go from the solid crystal to its separate ions. And just like our magnets getting pulled apart, that's always going to be a benefit when we go from the solid or from the separate ions to the solid. So we would prefer to be connected in one giant crystal as opposed to be apart in individual ions. And so that we always see that release of energy. Now, lattice energy depends on the size of the charges as well as the distance between them. The smaller the distance, the stronger the attraction. The larger the charge, the stronger the attraction. So both of those things matter. So this is NaCl over here. We should be able to figure out what color Na plus should be and what color Cl minus should be when we do our crystal structures. So this is going back to chapter 8 and our trends. So remember that whenever we become a cation means that we're losing electrons. And so a cation is going to be smaller than its neutral atom. And an anion is going to be larger because it's picking up. So if we wanted to look at our colors, green should be our chloride, and purple should be our sodium. Because the smaller one is going to be our positive, the larger one is going to be our negative. Now, when we're looking at an ionic bond, we've kind of discussed the different parts about it. We said, well, there's an energy that's required for us to ionize. So when we make all of our cations. And there's an energy involved with when we make our anions. For some elements, it takes us energy to make them into atoms. This would be things like chlorine going to just a chlorine by itself. And so that requires energy. And when we put these things together, we get a huge amount of energy that comes back when we make their solids. So when we put our ions together, and so when we look at this process, we can create something, and it's called the Born-Haber cycle. And what this is going to do is it's going to be a set of these hypothetical reactions that represents the formation of the ionic compound from its elements. Now, the reason why we're going to use this is because we can find the enthalpy of each of those reactions. And the very last one, we can use to find the energy of our lattice energy for that solid. And so this is an example of it. And so what I want you to do is take your time and try to identify which each of these steps is. So each of these transitions stands for one of those processes that we had talked about. It can stand for us getting those elements into their gaseous form. It can stand for us separating those elements so that they're in their atoms. It could be our ionization energy as we take that atom and we want to remove an electron. It could be the electron affinity as we add in an electron to it. And then we would have their overall lattice energy of our two ions as gases becoming a solid together. So when we're going through this, this first transition, this is us taking Na as a solid and going to Na as a gas. So kind of like if we were to vaporize, so first turn our solid into our liquid, a liquid into a gas for our sodium metal. So us to vaporize our sodium. This second one, this transition here, is what we require to take our chlorine from being Cl2 together to being two individual chlorine. So it's us breaking that bond in that chlorine-chlorine. Our next transition is us removing one electron from sodium, and that should be our ionization energy. And since we only need to do that once, then we only need one of those processes. On this second part, we've taken that electron, we've added it to that chlorine. So that's going to be the electron affinity. Now this, by definition, is what our lattice energy is. But when we look at this overall comparison, this reaction looks like Na as a solid plus 1/2 of a chlorine gas goes to NaCl as a solid. And we should be able to recognize that the name of this reaction is a heat formation. It's us making that NaCl, 1 mole of it, from its elemental form. So if we add up all of those other steps, it should be the same as us doing this transition for a heat formation. And so this is the Born-Haber cycle. We're going to add up all of our parts in order to figure out that lattice energy. And so those different parts have different things. They could be our ionization energies. They could be our electron affinities. They might be our delta HFs, right? And so this is an example where everything's kind of laid out for us. So you would want to make sure that you understood how to fill in one of these cycles, that if we were to give you things like the enthalpy change in the formation, right? So the heat of formation of our solid, and then I gave you the amount that needed to vaporize to form the gaseous or to break up the chlorine. We should be able to connect all of these into the circle so we could look for one unknown. That might be the lattice energy. It might be, we might know the lattice energy, but we might not know the heat of formation. So we should be able to work our way all the way through. And so the Born-Haber cycle is basically built off of Hess's law. Because the enthalpy change for each of these processes, we can do them in parts, or we can do them all at once, because the enthalpy change is going to be a state function. It's going to be path independent. So as you go through, we can start to cross out that all of our different steps that we've been doing with our reactants and our products, we can remove those. And you can see how our heats of formation should add up to all of those other things that we've done. And so we should be able to find the energy of that delta H for our lattice. Now there's some trends in our lattice energy. So know that your ion size, the larger the ion, the weaker their attraction is going to be. A larger ion means that there's larger distance between their positive and their negatives. The weaker the attraction, the smaller the lattice energy is going to be. So if we were to compare them, right, lithium, sodium, potassium, cesium, all of these have the same charge difference. It's all +1 and -1. So the thing that's changing isn't our chlorine size, it's the size of our cation, that lithium, that sodium, that potassium. And as the ion gets bigger, their distance between those charges also have to get bigger. And so you can see that their lattice energies decrease as our ion size gets bigger. Or I guess becomes less negative, might be a better term. The other part about that is going to be our charge. The larger the charge, the stronger the attraction is between them. It means that there's more ion, or there's more charge difference between those two. And so if we think back about our Coulomb's attraction, when that Q1 and that Q2 gets more negative, or sorry, when the charges increase, then this term here is becoming larger. And so our attractive force is also becoming larger. So between these two, they have similar distances apart, but this one has a higher or less, has a more negative lattice energy than our sodium, than a sodium fluoride, because it's got that larger charge. Now, Lewis theory generally says that the attraction between ionic compounds is large. It's why most of our ionic bonds are going to be solids. And so there's a couple of properties of our ionic compounds. They're hard and brittle and crystalline solids. They generally have really high melting points. Now, the interesting thing about ionic compounds is that in their solid state, they do not conduct electricity. But if you are able to melt them, then now you can conduct electricity, because now we have ions that are free to move around. Many of them are soluble in water, and when they disassociate inside of water, then they'll conduct electricity well, because when they dissolve, they separate out and they'll form ions, which will help us conduct the electricity. So in the solid, the ions are fixed in place, but once we get into a liquid, then those ions can move, or once we have them dissolved. Now, covalent bonds are something different. Covalent bonds occur when we have two nonmetals, and it's because we're going to share those electrons between those two atoms. And unlike an ionic bond, where that attraction is spread out between many different anions, covalent bonds are directional. They form between one atom and one atom. So covalent bond molecules form, or so covalent bonded atoms make up molecules. So they're called molecular compounds because they're going to be shared in the direction. And so normally we form discrete molecules, not just a big conglomeration. And the reason why they're directional is that they are formed by that attraction between those electrons and those nuclei. For an ionic bond, since we've already transferred those electrons, then those electrons are attached to one side or the other of the charge. For a covalent bond, because they're being shared, then we need to keep them in their best possible state, so between those two atoms that are sharing it. So the shared electrons hold the atoms together by attracting nuclei of both atoms. Now, Lewis theory focuses primarily on the valence electrons and their bonding, and we normally use Lewis theory for our covalent molecules. So valence electrons are held most loosely, and so that's why Lewis focused on them inside of our chemical reactions and our chemical bonding. Chemical bonding involves the transfer or sharing of those electrons between the two or more atoms. And so that's why they're primarily the most important inside of the bonding, because they're the ones that are held the loosest, and they're the ones that are more likely to engage inside of this transferring or sharing of electrons. So a Lewis dot diagram is a quick and easy diagram for us to show the valence electrons in an element. Now, a Lewis structure is normally the nucleus of the element is represented by its symbol, and then we have the number of valence electrons represented by dots around it. So there's a couple of terms that we're going to clarify. So an electron pair is going to be when two electrons are on one side of an electron. So this is an electron pair up on the top for our nitrogen. Your unpaired electrons is going to be those individual dots. So 6 dots represents 6 valence electrons, 5 dots represents 5. And so we're kind of using this symbol in the middle, this N or this O, to stand for all of our protons, all of our neutrons, and all of our core electrons. So the only thing that we have to worry about on the outside is our valence electron. Now, for Lewis's structures, there's 2 rules for when we do these symbols. One is that no side can have more than 2 dots. And the idea is that each orbital can only hold 2 electrons. And when we fill the sides, each side gets 1 dot before they double up. The only exception is hydrogen and helium, because these 2 only form 2 dots total, because they're the duet instead of the octet. So Lewis's bonding theory is based on this idea that atoms bond because it results in a more stable electron configuration. So when they say more stable, it means it's got a lower potential energy. This generally results in atoms trying to obtain 8 electrons, or this octet rule. There are some exceptions to this rule, but in general, what we're trying to do is collect an electron configuration similar to that of a noble gas. So if you remember, a noble gas has this configuration, NS2, NP6. So total, we have 2 electrons in our S plus 6 electrons in our P, and so that's where we get the octet from. There are a lot of different exceptions to this, and so we're going to be working through those. And so later on, we're going to get into what we call expanded, odd number ones, and incompletes. But we're going to start off with just some simple ones to begin with. So in the module, on our worksheet, in our lab, I've uploaded a worksheet that I want you to pull on up. And in our next video, we're going to work through that worksheet together as we start to practice how we draw those Lewis diagrams. And so we'll work through how we go through the bonding of those Lewis structures. And that way you have an opportunity to do some practice ones.